You are standing on a surface that will kill you in less than 2 minutes, and you do not even get the mercy of knowing which part of your body fails first. Maybe it is the pressure. Maybe it is the heat. Maybe it is the air itself turning your lungs into something closer to melted plastic. The universe is not gentle. It never was. Textbooks give you clean diagrams and rounded numbers, and none of that prepares you for what is actually out there. Picture iron falling sideways through the sky at thousands of miles an hour, not dripping down like rain, but blasted sideways by wind stronger than anything Earth has ever produced. Picture a moon smaller than our own moon, hiding twice the water of every ocean on this planet combined, sealed under ice in total darkness. If dangerous places pull at something in you, hit like and subscribe. Start close to home, because the nearest hell is only 2 planets away. Venus is almost Earth's twin in size and mass, close enough that early astronomers assumed it might be a sister world, maybe even a wetter, warmer version of our own. That comparison ends the moment you look past the numbers on a chart. Stand on Venus, and the air itself would crush you. Surface pressure there runs about 90 times what you feel at sea level on Earth. That is not a number you can picture as a number. Picture instead standing under half a mile of ocean water, the weight of that entire column pressing down on every inch of you at once. That is what the atmosphere alone would do to a human body on Venus, with no ocean involved at all, just air, thick and merciless. Now think about what that same pressure does to something built by human hands instead of flesh. 90 times sea level is roughly the pressure engineers plan for when they design submarine hulls meant to survive the deepest parts of Earth's oceans, and those hulls are built from steel and titanium, a foot thick in places, tested for years before anyone trusts them with a crew. A structure sitting on Venus's surface needs that same kind of shielding before it even accounts for the heat sitting right next to it. Metal does not usually fail cleanly under pressure like this. It deforms first, bending slowly before it gives way all at once, and a hull under that kind of strain has no warning before the moment it collapses. Add the heat on top of the crushing weight, you are no longer solving one engineering problem. You are solving 2 at the same time, a material that has to survive being squeezed and cooked simultaneously for as long as anyone needs it to keep working. Then there is the heat itself. Surface temperatures on Venus sit between 700 and 900 degrees Fahrenheit, hot enough to melt lead into a silver puddle on the ground. Mercury sits far closer to the Sun, and yet Venus runs hotter. Let that sink in. The planet nearer to the Sun is cooler than the one farther away. Distance did not decide this outcome. Something else did. Think of a car left in the sun with the windows rolled up. Heat gets in easily through the glass, but it cannot get back out the same way, so the inside keeps climbing past anything the outside air ever reached. Venus works the same way, except the windows are made of carbon dioxide, and the trapped heat never stops climbing. That is the runaway greenhouse effect, and the mechanism behind it is not one trick, but 2, feeding each other until neither one can be stopped. Carbon dioxide starts the process. It lets visible sunlight pass straight through to the surface, the same way glass does, but it blocks the infrared heat, trying to radiate back out afterward. More carbon dioxide sitting in the air means more heat trapped underneath it, a kind of one-way valve holding warmth in that would otherwise leak back into space. On its own, that mechanism raises a planet's temperature. Does not have to wreck the planet completely. The second piece is what turns a warm world into a dead one. As the surface heats, whatever ocean water still exists starts evaporating faster, and water vapor is an extremely effective greenhouse gas in its own right, arguably even more effective than carbon dioxide at trapping heat pound for pound. More evaporation means more water vapor in the sky. More water vapor in the sky means more heat trapped near the ground. More heat trapped near the ground means still more evaporation. That is the feedback loop, and it does not level off gently the way most physical processes do. Each step makes the next step worse, and nothing built into the process slows it down. Earth carries a mild version of that same loop right now. A hot day evaporates a little more water, which traps a little more heat, and the cycle folds itself into ordinary weather without spiraling into anything worse, because Earth sits far enough from the Sun that the loop never crosses its point of no return. Venus sat closer, warm enough from the start that the loop never found a place to stop. Water vapor kept climbing until whatever oceans Venus once held, if the models are right, boiled away completely, dumping their entire volume into the atmosphere as vapor, which trapped even more heat, which cooked away whatever liquid remained even faster than before. Here is the part that makes the whole mechanism permanent rather than temporary. That water vapor did not just sit in the sky forever. High in Venus's upper atmosphere, ultraviolet light from the sun split those water molecules apart, breaking them into hydrogen and oxygen. Hydrogen is light enough that much of it simply escaped into space, drifting off the planet for good, and taking with it any chance those molecules had of ever reforming as liquid water again. Venus did not just boil its oceans away. It lost the raw material for oceans entirely, bled off into the dark, atom by atom, until there was nothing left to rebuild them, with even if the planet somehow cooled back down tomorrow. That is the threshold this planet crossed. Not simply heat, but the point past which the ingredients for undoing that heat no longer exist at all. We know some of this firsthand, because humans actually sent machines down to check. The Soviet Union and a program called Venera, through the 1960 seconds, 70s, and into the 80s, throwing spacecraft at Venus one after another, to find out exactly how bad conditions were on the ground. Probe after probe got crushed or cooked before reaching the surface at all, and each failure forced engineers back to the drawing board for thicker shielding, tougher seals, cooling systems built to buy a few more minutes against heat that never lets up even slightly. Venera 7 became the first machine from Earth to reach Venus's surface and send anything back. It survived roughly 23 minutes before the heat and pressure finished it off, just long enough to confirm temperature readings that had seemed almost too extreme to trust beforehand. Venera 9 went further and sent back the first photograph ever taken from the surface of another planet, a grainy image of flat, sharp-edged rocks stretching under a strange orange sky, lit not by a clear sun, but by light filtered through haze, so thick it turned midday into something closer to a permanent overcast afternoon. Venera 13 lasted longest of the entire program, transmitting data for about 2 hours before the same fate caught up with it, cooked and crushed at once, its instruments failing one after another, as the surface conditions finally won. What those 2 hours brought scientists was extraordinary. Venera 13 measured the surface rock directly and confirmed basalt similar to volcanic rock found on Earth. Its cameras captured color photographs of a landscape, the color of rust and iron, flat slabs scattered across a plain with no visible sign of erosion by wind or water, because there was no water to erode anything, and the wind down at the surface barely moves at all despite the ferocious speeds recorded higher up in the atmosphere. Every lander in the Venera program was built knowing it was going to die on the surface. Engineers designed a machine, aimed it at a planet, and treated 2 hours of survival as a triumph. That is the kind of place Venus is. Human hardware, built to survive some of the harshest environments on Earth, arrives there and starts dying on a clock. And everyone involved considers that a successful mission. Venus keeps one more secret that has nothing to do with heat or pressure at all, and it sits in the way the planet spins. Nearly every planet in the solar system rotates the same general direction it orbits the Sun. The way a top spins after you flick it forward, Venus spins backward. Look down at the solar system from above its north pole, and every other major planet turns counterclockwise. Venus turns clockwise, alone the odd rotation out among all 8 planets. That backward spin is called retrograde rotation, and it is not even the strangest part of Venus's relationship with time. A single day on Venus, meaning one full rotation on its own axis, takes about 243 Earth days to complete. A single year on Venus, one full trip around the Sun, takes about 225 Earth days. Sit with that arithmetic for a second. Venus's day is longer than its year. The planet finishes an entire orbit around the Sun before it finishes spinning once on its own axis. An arrangement that shares nothing with the tidy ratio of day to year we take for granted here. Combine the slow backward spin with that mismatched timing, and something genuinely strange falls out of the math. Because Venus rotates backward, a full solar day there, sunrise to sunrise rather than one bare rotation, actually ends up shorter than the planet's own year, landing at around 117 Earth days. The Sun there would rise in the west and set in the east, crawling the reverse direction from every sunrise anyone on Earth has ever watched, if you could even see it at all through that choking haze overhead. Nobody has a fully settled explanation for why Venus ended up spinning this way. One leading idea points to an ancient, massive collision early in the planet's history, an impact violent enough to knock its rotation into reverse and leave it there permanently. The same kind of event thought to have tilted other planets and moons during the solar system's early chaotic years. Another idea points to Venus's own atmosphere, thick and heavy enough that atmospheric tides, the drag of that dense air interacting with the planet's rotation over billions of years, could have slowly dragged the spin down. Both explanations remain live possibilities. Neither has been confirmed. The axial tilt adds one more layer on top of the backward spin. Venus's axis sits tilted just a few degrees off, being completely upside down relative to its orbit, meaning this planet is close to lying on its side, compared to where you would expect its poles to point. Combined with the retrograde spin, some scientists describe Venus as a world that got flipped over entirely at some point in its past, rotating in reverse with its axis nearly inverted. Everything about it knocked backward at once and never righted since. Above all that heat and all that strangeness sits a deck of clouds that has nothing to do with water at all. Venus's cloud layer runs from roughly 30 miles above the surface up to around 40 miles, a thick, unbroken haze wrapping the entire planet in a shroud that never clears and never lets a single beam of direct sunlight reach the ground below. Point even the most powerful telescope at Venus, and that haze is all you will ever see. A planet's true surface, hidden completely behind clouds that admit no gaps at all. Those clouds are built from sulfuric acid rather than water, a chemical corrosive enough to dissolve most metals and destroy human tissue on contact within seconds. The process starts with sulfur dioxide, a gas pumped into Venus's atmosphere in enormous quantities by the planet's own volcanic activity, apparently still ongoing in some form today. High in the atmosphere, ultraviolet light from the sun breaks that sulfur dioxide apart and drives reactions that combine the leftover fragments with water vapor and oxygen, manufacturing sulfuric acid droplets suspended in the sky the way water droplets form clouds back on Earth. From space, the result looks pale and almost gentle, a soft yellowish white wrapped around the whole globe, giving no hint of the corrosive chemistry churning inside it. Rain does fall from those clouds, and this is where Venus does something no other planet in this story quite matches. Droplets of sulfuric acid form high in that cloud deck and start falling the way any rain falls, pulled down by gravity toward the surface below. They never arrive. Temperature climbs so sharply in the lower atmosphere that those droplets boil back into vapor partway down, evaporating completely before gravity can finish the job of delivering them to the ground. Scientists call this virga, rain that vanishes before it lands, and Venus produces virga on a planetary scale, an entire deck of clouds endlessly raining into empty air that never receives a single drop. A storm that begins every day and finishes nothing forever, because the world underneath it is too hot to let rain exist as rain past a certain altitude. Here is the detail that makes Venus feel less like an alien world and more like a warning. NASA climate modeling suggests Venus may have held oceans and livable temperatures for as long as 2 billion years, a span longer than complex life has existed on Earth. Run that model forward, and the early picture looks almost gentle. A thinner atmosphere than today's real clouds. Instead of choking sulfuric haze, shallow oceans spread across a rocky surface, not so different from Earth's own early years. Sunlight reaching a ground that was not yet trying to kill anything standing on it. Something broke that balance, and the leading suspect is the same one driving nearly every other feature of this planet. Slow, steady volcanic activity kept adding carbon dioxide to Venus's atmosphere over hundreds of millions of years, a trickle rather than a single catastrophic event. Quietly, the greenhouse effect crept upward. At some point, likely somewhere between 700 million and a billion years ago, based on current modeling, the balance crossed its threshold. Oceans that had existed for a billion years or longer began evaporating faster than they could be replenished, triggering the feedback loop that had been sitting dormant the entire time, waiting only for the temperature to reach the point where it could no longer be undone. What makes this genuinely unsettling is how slow the whole collapse was. This was not an asteroid impact or a single violent event with a clean before and after. This was a planet drifting gradually toward a line it could not see, crossing it, and only afterward discovering that everything on the other side of that line accelerated on its own. By the time the feedback loop took hold, no mechanism remained to reverse it. The oceans vanished within what may have been a geologically short window, and the atmosphere that replaced them locked the whole planet into the furnace it still is today. Earth is not Venus, and nothing here argues that Earth is on the same path. But the mechanism itself does not care which planet it runs on. It cares about thresholds, about the balance between how much heat arrives and how much heat manages to escape again, and about how much feedback sits waiting in reserve once that balance tips. Venus is proof that a rocky planet sitting at a survivable distance from its star, holding oceans for a span longer than life has existed here, can still cross that threshold and never come back. The line exists. Venus found it. So what flips a habitable world into something like this? What is the line between a planet that keeps its balance and one that loses it completely and never finds it again? Move outward past Mars, past the asteroid belt, and the next stop does not even offer you a floor. Jupiter has no solid surface anywhere inside it. Not hidden under clouds, not buried deep beneath layers of gas. There is simply no ground to reach ever, no matter how far down you go. Picture jumping into Jupiter with no ship, no parachute, nothing to stop your fall. You would not hit anything. You would just keep sinking, and the deeper you sank, the worse everything around you would get. The first layer swallows you almost gently. Up near the cloud tops, Jupiter's atmosphere is mostly hydrogen and helium, thin enough that a falling body would drop through it the way a skydiver dropped through Earth's air, just far colder than anything you have ever stood in, somewhere near 230 degrees below 0 Fahrenheit. The clouds here are made of ammonia ice, pale and streaked, and they are the only part of Jupiter any camera has ever actually photographed. Everything below this point is inference, built from pressure readings and magnetic data, rather than a single direct image. Keep falling, and the gas stops feeling like gas within a couple hundred miles. Pressure builds fast, faster than intuition wants to allow. Somewhere around 10 times the pressure you feel at Earth's surface, hydrogen starts behaving strangely, thickening, resisting. No longer just gas, but not yet anything you would call liquid either. Temperature is climbing too, and it does not stop. A few hundred miles down, the environment around a falling body would already be hot enough to glow, in some models approaching the temperature at the surface of the sun, even though there is no sun anywhere nearby to explain that heat. The heat is coming from the crushing itself, from gas being squeezed by everything sitting above it. Go deeper still, thousands of miles down, and hydrogen finishes its transformation into something with no equivalent on Earth's surface at all. It becomes a hot, dense fluid, still technically hydrogen, but behaving like a liquid under pressures that would flatten a submarine hull into foil in an instant. A human body would not survive long enough to register any of this. Long before the exotic chemistry sets in, the pressure alone would have crushed the chest cavity and stopped circulation, all within the first few hundred miles of falling. Deep enough into that descent, hydrogen itself changes into something almost unrecognizable. Roughly halfway to Jupiter's center, at pressures estimated near several million times what you feel standing on Earth's surface, hydrogen atoms get squeezed so hard that their electrons stop belonging to individual atoms at all. They go free, drifting through the fluid the way electrons drift through copper wire. That is what makes this stuff conduct electricity the way a metal does. Scientists call it metallic hydrogen, and it exists nowhere on Earth in any natural form. Laboratories have managed to create tiny fleeting flashes of it under extreme compression, lasting a fraction of a second before the sample destroys itself. Jupiter holds an entire ocean of it permanently, layers deep inside a planet with no ground to stand on. This metallic hydrogen layer is not some minor footnote. It likely makes up the bulk of Jupiter's interior by volume, a churning, electrically conductive fluid, tens of thousands of miles deep, hot enough in places to rival stellar temperatures, all of it moving, all of it under pressure. No material built by human hands has ever been tested against and survived. For decades, the assumption was that underneath all of that metallic hydrogen, at a small, dense, clearly defined rocky core, something like an oversized version of Earth wrapped inside a gas giant. The Juno spacecraft, orbiting Jupiter since 2016 and mapping its gravity field with extraordinary precision, found something messier instead. Rather than a sharp boundary between core and metallic hydrogen, Juno's data suggests the core is diluted, its heavy elements mixed and smeared out over a huge portion of the planet's interior, rather than sitting in a tight, separate ball at the center. Some models describe it as fuzzy, a core with no clean edge, blended into the surrounding hydrogen the way cream stirred halfway into coffee, refuses to stay in its own separate layer. It came straight out of the data, and scientists are still working out what event in Jupiter's early history could have mixed a core that thoroughly. Juno was not built to study the interior alone. It was also built to look straight down into the Great Red Spot, and what it found there rewrote assumptions that had stood for decades. People have been watching this storm for a very long time. Observations that may show the Great Red Spot go back to the 1,600 seconds, when astronomers using some of the earliest telescopes ever built recorded a persistent dark oval sitting in Jupiter's southern hemisphere. Whether that exact feature is the same storm raging today or an earlier storm that faded while a new one took its place around the same latitude is still debated. But continuous confirmed tracking of the Great Red Spot stretches back at least 1,550 years without a real gap. Either way, this is not a storm that formed last century. It is one of the oldest continuously observed features anywhere in the solar system. It has not stayed the same size the whole time. Measurements from the late 1,800 seconds describe a storm wide enough to fit close to 3 Earths across its diameter. Today it has shrunk to something closer to the width of a single Earth, still enormous, still capable of swallowing this entire planet whole, but noticeably smaller than the storm astronomers were sketching by hand more than a century ago. Modern telescopes and spacecraft have tracked that shrinkage year by year, watching the oval slowly tighten and grow more circular, and nobody has a fully settled answer for why. Some models point to smaller vortices getting absorbed into the main storm and disrupting its structure. Others point to changes in the deeper flows feeding it from below. The storm is shrinking in plain view, and the mechanism behind that shrinkage is still an open question. Cassini, passing Jupiter in 2000, on its way to Saturn, captured some of the sharpest images of the storm taken up to that point, showing turbulent structure at its edges, smaller storms getting shredded and absorbed into the larger one like debris caught in a drain. But it was Juno, flying directly over the Great Red Spot in 2017 with instruments built to peer beneath the visible cloud tops, that answered the deeper question: how far down does this storm actually reach? The answer surprised almost everyone working on the mission. Juno's data suggests the Great Red Spot extends somewhere between 200 and 300 miles beneath the visible clouds, a storm with roots driving deep into the planet rather than a shallow surface feature skimming across the top of the atmosphere. That is not a hurricane in any sense Earth produces. Earth's hurricanes stay shallow by comparison, confined to the lowest layer of the atmosphere. This storm reaches down toward pressures and temperatures that would already be lethal to anything built by human hands, and it has been doing that for centuries without pause. Try to hold the scale of it in your head all at once. The storm alone, not the planet, just the storm, is wide enough to fit more than one Earth across its face, with room left over at the edges. Wind speeds at its outer boundary have been clocked at more than 400 miles an hour, ripping around the storm's perimeter while the center rotates more slowly, a structure closer to a wheel within a wheel than anything resembling a single simple gust. And this has been running continuously, spinning, absorbing smaller storms, slowly shrinking for longer than any government on Earth has existed in its current form. Try to hold the size of the whole planet in your head for a moment. More than 1,000 Earths would fit inside Jupiter's volume. That is not a comparison meant to sound impressive. It is meant to make you feel small, because you are. None of this, the storm, the metallic hydrogen, the crushing interior, would matter as much to the space around Jupiter, if not for what all that churning metal actually generates. Metallic hydrogen does not just sit there conducting electricity quietly. Its motion, stirred by the planet's fast rotation, a full spin every 10 hours, despite Jupiter's enormous size, generates a magnetic field on a scale nothing else in the solar system can match. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, and it does not stay politely close to the planet the way Earth's field does. It balloons outward for millions of miles, wrapping around every one of Jupiter's major moons and trapping charged particles into radiation belts so intense would kill an unshielded human within minutes. Earth's magnetic field comes from roughly the same basic mechanism, a churning conductive layer deep inside the planet, in our case molten iron rather than metallic hydrogen, generating a field through motion and rotation. The difference is scale. Earth's field deflects the solar wind and paints the sky with auroras at the poles. Jupiter's field does that too, but at a size and intensity that turns the entire neighborhood around it hostile. Europa sits bathed in that radiation constantly. Io, Jupiter's innermost large moon, gets squeezed by gravity and scoured by that same magnetic environment so hard that it has become the most volcanically active body in the solar system. Its surface repainted by eruptions faster than any other world humans have ever mapped. Jupiter's magnetic field even links to Io directly through something scientists call a flux tube, a standing electrical current flowing between moon and planet strong enough to drive aurora-like glows at Jupiter's own poles tied to Io's exact orbital position. None of that space around Jupiter is calm. It is dense with radiation, threaded with electrical currents, shaped entirely by the same metallic ocean, churning inside a planet with no surface at all. From the outside, almost none of this looks like violence. Jupiter looks calm, banded, almost decorative, with its swirling stripes of orange and cream. This is the largest planet in our solar system, and it is only the beginning of what waits farther out. Because past Jupiter, past Saturn's rings, the planets do not get gentler. They get colder, and somehow they get faster. Wind out there does not just blow, it tears. Keep going outward, and the temperature drops, but the violence does not. Neptune sits nearly 3 billion miles from the Sun, wrapped in a deep blue haze that looks calm the way still water. Looks calm right before you learn how cold it is. Measure the wind there, and the number stops making sense. Neptune's winds reach close to 1,200 miles an hour, the fastest sustained winds recorded anywhere in the solar system. Try to place that number next to something you already know. The strongest hurricanes that ever form on Earth top out somewhere around 200 miles an hour, and those are the storms that flatten coastlines and get named and remembered for decades. Neptune's winds run 6 times faster than that, all the time, with no eye of calm at the center and no coastline to eventually weaken them. There is nothing to slow it down out there. No mountain range, no friction from solid ground. Nothing but gas circling a planet that barely gets enough sunlight to cast a decent shadow. The cold should calm things down. Nobody measured those winds by holding an instrument up to the sky. Scientists clocked them by watching clouds move. Neptune's atmosphere carries streaks of frozen methane drifting across its face, bright enough against the deep blue backdrop to track from one image to the next. Time how far a cloud feature travels between 2 photographs, taken minutes apart, and you get a speed. Do that across thousands of cloud features at different latitudes, and you get a map of how fast the entire atmosphere is moving, band by band, layer by layer. That is how 1,200 miles an hour stopped being a guess and became a measurement written down in a logbook. The spacecraft that did most of that measuring only got one chance to do it. In August of 1989, after a 12-year journey that had already carried it past Jupiter, Saturn, and Uranus, Voyager 2 swept past Neptune at a distance of about 3,000 miles, the closest any spacecraft has ever come to this planet, and the closest any spacecraft is scheduled to come again anytime soon. There is no follow-up mission on the books. Every photograph, every wind reading, every scrap of close-up data humanity has ever collected on Neptune came from that single pass decades ago, and nothing since. What Voyager 2 found rewrote the assumptions scientists carried into the flyby. The working guess beforehand was simple. A planet this far from the Sun, running on sunlight roughly 900 times weaker than what reaches Earth, should have a slow, quiet atmosphere. Cold was supposed to mean calm. Neptune's sky was in constant upheaval, streaked with fast-moving cloud bands and churning storms, wind speeds that made no sense at all for a world running on this little incoming energy. That contradiction points straight at one of the strangest open questions about Neptune. It has stayed open since that 1989 flyby. Neptune radiates roughly 2.5 times more heat than it receives from the Sun. Read that again, because it runs backward from how a planet is supposed to work. Sunlight arrives at Neptune as barely more than a bright star in a black sky, and yet the planet is putting out more energy than that faint light is delivering. Something inside Neptune is generating heat on its own, and nobody has nailed down exactly what. A few explanations compete for the answer. One points to leftover heat from Neptune's own formation, energy trapped since the planet first came together billions of years ago, still leaking out from the core the way embers hold warmth long after a fire stops burning. Another points to something happening in the interior right now. Methane, or other compounds shifting under crushing pressure and releasing energy as a byproduct, a slow-motion reaction running at planetary scale. A third points to gravitational settling, heavier material still sinking toward the core even today, converting that fall into heat the same way anything releases energy when it drops. None of these has been confirmed outright. What is confirmed is the imbalance itself, and an atmosphere violent enough to suggest that extra heat is doing real work up at the cloud tops. Uranus, one planet closer to the Sun and similar in size and makeup, does not show this same imbalance nearly as strongly, which only deepens the mystery. Two ice giants, built almost the same way, and only one of them runs a hidden furnace underneath. Voyager 2 caught something else during that single pass, a storm that briefly made Neptune look like a smaller, colder echo of Jupiter. Scientists named it the Great Dark Spot, a storm system roughly the size of Earth, dark against Neptune's blue the way Jupiter's storm glows red against its own bands. For a moment the comparison seemed obvious. Two giant planets, two giant storms, similar scale, similar shape. Then the differences started showing up. Jupiter's Great Red Spot has been tracked continuously for at least 150 years. A storm old enough to have been sketched by astronomers using some of the first telescopes ever pointed at the sky. Neptune's Great Dark Spot did not have that kind of staying power. When the Hubble Space Telescope looked for it again in 1994, only 5 years after Voyager 2 photographed it, the storm was gone. A new dark spot had formed in the opposite hemisphere instead. A different storm entirely, as if Neptune resets its entire storm system on a timescale of years rather than centuries. That difference matters more than it sounds like it should. Jupiter's storm survives because it runs deep-rooted, hundreds of miles down into the planet's interior, drawing on a structure that does not shift quickly. Neptune's storms behave more like weather in the way Earth understands the term, transient, forming and dissolving over a handful of years, driven by an atmosphere that churns and reorganizes itself on a far faster clock. Nobody has fully explained why one giant planet storm holds together for a century and a half, while the others can vanish inside half a decade. What is clear is that Neptune's atmosphere is not just violent. It rewrites its own weather map on a schedule closer to a human lifetime than a geological one. Saturn tells a different version of the same story. Calm from a distance, chaotic up close, except Saturn keeps features that show up nowhere else in the solar system at all. Start at the top of the planet at its north pole, where Saturn holds something that looks almost designed on purpose. A hexagon. Not a round, polar vortex the way most rotating planets produce, but a six-sided jet stream wrapping the pole in straight edges and sharp corners, wide enough that 4 Earths could fit inside it side by side. Voyager caught the first hints of it in the early 1982, and the Cassini spacecraft spent over a decade photographing it in detail after arriving at Saturn in 2004, watching that six-sided shape hold year after year, a straight-edge pattern. Nobody fully agrees on why the hexagon keeps that shape instead of rounding out into a circle the way spinning fluids usually do. Laboratory experiments on Earth have recreated hexagon-like patterns by spinning fluid at specific speeds relative to a slower surrounding layer, suggesting the shape comes from different wind speeds at different latitudes. Whether that lab result fully explains Saturn's real hexagon is still debated. What is not debated is that it has held its shape for as long as spacecraft have been watching it, decades running. A permanent geometric scar sitting on top of a planet that otherwise looks as soft as anything in the solar system. Saturn keeps a second kind of storm in reserve, one that does not show up constantly the way the hexagon does, but returns on a rhythm of its own. Roughly every 30 years, Saturn produces what astronomers call a great white spot, a storm system that does not stay contained to one region the way Jupiter's great red spot does, but spreads until it wraps entirely around the planet, a band of churning white cutting across Saturn's calm gold bands like a wound circling the whole body. These storms have been recorded going back to at least 1876, reappearing in 1903, 1933, 1960, 1990, and 2010, close enough to that 30-year rhythm that scientists suspect something cyclical deep in Saturn's atmosphere builds toward eruption on a schedule, even if nobody can yet say what that mechanism actually is. The 1990 storm was large enough for backyard telescopes on Earth to see directly. The 2010 storm, tracked in far more detail because Cassini was already in orbit when it erupted, grew until it stretched around the entire planet, visible as a bright band circling Saturn's globe for months before it finally faded out. Underneath both the hexagon and the great white spot sits Saturn's jet stream structure, dozens of distinct wind bands running at different speeds and sometimes different directions, stacked on top of each other, banding the planet the way Jupiter's own jets do. Gusts strong enough to circle the entire planet in a matter of hours. From a distance, all of that shows up as nothing more than soft gold and cream stripes, gentle looking, almost decorative. Up close, every one of those stripes is a wall of wind moving faster than anything Earth's atmosphere has ever produced, sitting next to other walls of wind moving at entirely different speeds, shearing against each other in bands that circle the planet without ever stopping. That is the real lesson both Voyager flybys left behind at Neptune in 1989 and at Saturn years before that. Before those spacecraft arrived, the outer solar system was mostly guesswork, dots of light studied through telescopes too far away to resolve real detail, distant enough that violence and calm looked identical from here. Voyager changed that simply by getting close enough to see the difference, and what it found was that distance had been lying the entire time. Every one of these worlds looks serene from where we stand, blue marbles and gold-ringed jewels hanging still against the dark. Get close enough, the way Voyager did just once, for each of them, and serene stops being the right word for any of it. Neptune's calm blue face hides sustained winds strong enough to flay skin from bone in seconds. Saturn's soft rings and gentle banding hide a jet stream structure violent enough to circle the planet in hours, and a storm cycle that occasionally wraps the entire globe in raw, churning weather. That is the trait both worlds share, and it is worth sitting with for a moment. Hostile beauty. From a distance, Neptune looks like a marble, smooth and blue, and almost gentle. Saturn looks ornamental, built for admiration rather than danger. Get close enough to either one, and the picture changes completely. Distance is doing a lot of the work in making these planets look safe. Strip the distance away, and what is left is wind that would flay skin from bone in seconds, cold enough to make the wind itself feel like a blade, and a pair of storm systems, one vanishing inside 5 years, one returning every 30, that neither planet has any obvious reason to produce at all. And this is still our own solar system. This is still the neighborhood, the planets we have mapped, orbited, photographed up close with our own spacecraft. Out past our sun, past the reach of anything we have physically touched, the planets stop playing by even these rules. Somewhere out there is a world where the glass in the sky falls sideways. Somewhere is a planet raining metal. Somewhere is a planet so strange it makes Jupiter's storms and Neptune's winds look almost quaint by comparison. To see those worlds at all, we first have to understand the trick that lets us look at something we can never touch. Here is the problem nobody talks about when they show you a picture of an exoplanet online. That picture is fake. Not fake in the sense of dishonest, but fake in the sense that no camera anywhere has ever taken a real photograph of most of these worlds. They sit too far away, too close to stars that outshine them by billions of times. So how do we know any of this? How do we know what gas fills a sky we will never fly through? The answer comes down to a trick called transit spectroscopy. And once you understand it, everything else in this story makes sense. A planet crosses in front of its star from our point of view, and for a few hours, a sliver of starlight passes straight through that planet's atmosphere on its way to us. Think of sunlight cutting through fog on a cold morning. The fog does not stop the light completely. It changes it, scatters some wavelengths, lets others through clean. Starlight does the same thing passing through an alien sky. Every gas in that atmosphere eats a specific slice of light, a fingerprint written into the spectrum. Read the missing wavelengths, and you are reading the ingredients list of a world hundreds of light years away. Why not just point a telescope and look directly at the planet? Because a planet next to its star is like a firefly parked an inch from a stadium spotlight. The light drowns it. Every direct attempt to photograph most of these worlds fails for that exact reason. The glare erases anything small and dim, standing that close to something so much brighter. This is where the James Webb Space Telescope changes the entire conversation. Webb was built to catch light so faint it borders on nothing, and when it turns toward a transiting planet, it can pull a clean chemical signature out of a whisper of starlight that older instruments could barely register. For the first time, scientists were not guessing at alien atmospheres from theory alone. They were reading them directly. And going into this, scientists had a decent idea of what they expected to find. Models built from physics and chemistry predicted which gases should appear, at which temperatures, which clouds should form, where, which planet should look calm and which should look violent, Webb turned toward those planets ready to confirm the models. Instead, one of the very first worlds it studied handed back a molecule that should not have existed there at all. The planet that broke the models first is called WASP 39b, and it does not waste time getting close to its star. This is a bloated gas giant, puffed out and loose, circling its sun at a distance closer than Mercury ever gets to ours. A year there lasts 4 days. Not 4 months, not 4 Earth years, 4 days. Start to finish, the entire orbit complete before a normal work week would even end back home. That kind of closeness comes with a cost. Dayside temperatures on WASP 39b sit near 1,600 degrees Fahrenheit, hot enough to melt silver into liquid. Any chemistry happening in that atmosphere is happening under conditions closer to a blast furnace. Here is where the story gets strange. When scientists pointed Webb at this planet and read the chemical fingerprint bleeding through its atmosphere, they found sulfur dioxide sitting right there in the data, clear and unmistakable. That should not have been possible. Sulfur dioxide is a fragile molecule, the kind of thing that gets torn apart almost instantly at temperatures anywhere close to 1600 degrees. It has no business surviving in an atmosphere that hot, let alone showing up in strong enough concentration for a telescope hundreds of light years away to catch it. So how does a fragile molecule survive in a furnace built to destroy it? The answer is not that the molecule survived the heat. The answer is that the heat had nothing to do with it. Starlight itself was building the molecule fresh, breaking other compounds apart and welding the leftover pieces into sulfur dioxide in real time, faster than the heat could tear it back down. Scientists call this process photochemistry, and it is not some exotic idea invented for this planet. It is the same basic mechanism sitting above your own head right now. Sunlight striking oxygen molecules high in Earth's atmosphere builds the ozone layer through this exact process, breaking bonds and forging new ones under nothing but the push of light. The haze hanging over a city on a hot afternoon runs on the same principle. Sunlight cooking raw ingredients into something new that was not there that morning. WASP 39b was doing this on a scale and under conditions Earth never sees, but the physics driving it was identical. Starlight was not just heating that atmosphere. It was building it, chemical bond by chemical bond, in a constant cycle of destruction and creation happening every second the star's light kept hitting that thick, boiling sky. This was the moment atmospheric chemistry on another world stopped being theoretical. WASP 39b became the first confirmed case of an alien atmosphere with active, ongoing chemistry. Gases being manufactured rather than simply inherited from formation billions of years ago. The sky itself was alive with reactions. And if starlight alone could build molecules that should not survive on one planet, the next question writes itself. What happens when that same trick shows up on a world already strange enough to break every other rule in the book? The stranger planet has a name that sounds like it belongs in a candy shop instead of a physics journal. WASP 107b. Scientists nicknamed it the Cotton Candy Planet, and once you hear the numbers behind that name, the nickname stops sounding cute and starts sounding unsettling. This world is roughly the size of Jupiter, wide enough to fill the same amount of sky. But its mass is only about 1/10 of Jupiter's same size, a fraction of the weight. Picture 2 boxes, the exact same dimensions, one packed solid with books, the other stuffed with foam packing peanuts. They look identical from across the room. Pick them up, and the difference becomes obvious immediately. Here is how light this planet actually is. If you built an ocean large enough to hold it, Washington SB Pond and 7B would float, not sink partway and settle, not bob awkwardly at the surface. Float the way a beach ball floats, an entire gas giant riding on top of water, because its overall density is lower than water itself. A planet built more like a cloud than like a world. When scientists pointed Webb at this puffed out ball of gas and read the light bleeding through its atmosphere, the chemical barcode came back thick with detail. Water vapor showed up first, unsurprising for a gas giant this size. Sulfur dioxide followed, the same photochemical fingerprint already caught on WASP-39b, proof that starlight-driven chemistry was not a one-planet fluke. Then carbon dioxide. And, threaded through all of it, something stranger still. Silicate clouds, tiny grains of vaporized rock, drifting through the sky where water droplets should be. That alone would have made headlines. But the detail that actually stopped researchers cold was a gas that was supposed to be there and was not. Every model built for a planet this size and this temperature demanded methane. Not a trace of it, an abundance of it. Cooler gas giants are supposed to be soaked in the stuff, the same way Jupiter and Saturn carry heavy concentrations of methane in their own skies. Webb looked for it on WASP-107b and found almost nothing. A whisper where a flood should have been. So what erases a gas that basic chemistry says should be everywhere? The answer, scientists landed on points straight down into the planet's own interior. If heat is rising from deep inside WASP-107b, far more heat than a planet this size should be generating on its own, that internal engine would drag carbon-rich material up from the depths before it ever had the chance to settle into methane. The molecule gets destroyed in transit, torn apart by rising heat before it can even finish forming. Not blocked from existing. Prevented from existing over and over in a constant churn between the planet's hot interior and its outer atmosphere. That explanation solves one mystery and opens a bigger one immediately behind it. Why is the inside of this fluffy, lightweight planet running hot enough to erase methane before it forms at all? A planet this loosely packed should have cooled long ago, settling into something calm and quiet. Instead, something down in the dark is keeping the furnace lit, strong enough to reach all the way up and rewrite the chemistry of the sky above it. Nobody has a confirmed answer yet. What is certain is that the heat is real, the effect is measurable, and it is not staying contained where it started. That same rising heat that erased the methane is the same heat, now building something else entirely above it, drifting through the upper atmosphere in a haze that has never been confirmed on any other world. Follow that heat upward and it does not just erase methane. It builds something else entirely, something drifting through WASP-107b's upper sky that has never been confirmed on any other planet before this one. Silicate clouds, not water, not ice. Grains of vaporized rock, cooked out of the deep atmosphere and floating high above the surface in a haze made of what would be sand or glass anywhere else in the universe. Picture what a cloud is supposed to be. On Earth, water evaporates off an ocean, rises, cools, and clumps into soft droplets that catch light and drift without weight. Gentle enough that a plane can cut straight through one without a scratch. Now strip that comfort away completely. On WASP-107b, the material forming the clouds is rock, silicon and oxygen, the same basic ingredients baked into window glass and beach sand, boiled off the planet's own interior and carried up into the sky as vapor before the cold of altitude locks it back into solid grains. Fly through a cloud like that, and you would not feel mist against your skin. you would feel sandpaper, moving at altitude, a haze that scrapes rather than soaks, hot enough at the edges to blister, and hard enough at the center to scratch. Nothing about it would feel soft. Every part of it would feel like it was trying to wear you down, one grain at a time. The cycle behind it runs on a rhythm as simple as it is violent. Deep in the atmosphere, heat rising from below vaporizes rock the same way a stove boils water. Except the boiling point here sits at temperatures that would liquefy steel. That vapor rises, thins out, and hits cooler air higher up, where it cannot stay a gas any longer. It condenses, not into droplets, but into fine solid grains, the same transformation water makes, turning to frost on a cold window, except the frost here is made of glass. Those grains grow heavy enough to fall, drifting back down through the sky, as a kind of rain no planet in our own solar system has ever produced. It lands, it meets the heat again, it boils back into vapor, and the entire cycle restarts from nothing. A weather system with no season, no beginning, no end. Just vaporizing, cooling, falling, vaporizing again forever, driven by whatever furnace is running underneath. What makes this discovery matter beyond one strange planet is the fact itself. This is the first time scientists have directly detected silicate clouds in the atmosphere of any exoplanet anywhere, not inferred from a model, not guessed at from indirect data. Read straight out of starlight, passing through an alien sky. Confirmed the same way the missing methane was confirmed. Chemical fingerprint by chemical fingerprint, and the heat responsible for all of it. The same internal furnace-destroying methane and cooking rock into cloud is not something unique to this one bloated, oversized world. Planets like WASP-107b keep turning up across the galaxy in growing numbers, each one just as puffed out, just as strangely warm on the inside as it has no right to be. That pattern has a name now, and it is bigger than any single planet. Gas giants are supposed to get smaller as they get older. That is not a guess, that is basic physics playing out the same way it does everywhere else in the universe. A planet forms hot, glowing, with the leftover energy of its own creation, and over billions of years it cools. As it cools, it contracts, gravity pulling the whole structure in tighter the way a fire shrinks down to embers as the heat drains out of it. Jupiter has been doing this for 4.5 billion years. Saturn too. Every gas giant we understand well follows the same arc. Hot and large in youth, cooler and tighter with age. WASP-107b refuses to follow that arc. It should have shrunk by now. Instead, it stays bloated, holding on to a size that only makes sense for a planet fresh out of formation, not one that has had billions of years to settle down. And it is not alone. Across the galaxy, more and more of these puffed out worlds keep turning up in survey after survey. Planets that by every rule of planetary aging should be smaller, denser, quieter than they actually are. Scientists have a handful of competing explanations, and none of them has won outright. One idea points to the star itself. Tidal forces from a close orbit flexing the planet the way Jupiter flexes its own moons, pumping energy in through pure gravitational squeezing. Another idea points to something unseen, a hidden companion planet tugging at the puffy world from a distance, stirring its interior without ever showing itself directly. A third idea blames the sky rather than the interior, a layer of haze sitting high in the atmosphere that traps heat the way a blanket traps warmth, keeping the whole planet inflated from the outside in. And a fourth idea is stranger still, suggesting some of these worlds might carry ring systems large enough to throw off the measurements entirely, making a smaller planet look artificially larger than it really is. Each theory demands different chemistry, different heat patterns, different signatures buried in the light passing through these atmospheres. That is exactly why Webb matters here. For the first time, scientists are not stuck choosing between competing guesses. They can read the atmospheric chemistry directly, compare it against what each theory predicts, and start ruling explanations out one by one instead of debating them on paper alone. The puzzle of why these planets refuse to shrink is still open. But somewhere in that same unresolved puzzle sits a planet whose winds are so extreme they do something even stranger than staying inflated. They erase the very idea of day and night. A planet this close to its star does not get to keep its own rotation. Gravity locks it in place, the same grip Earth's moon feels from us, and the result is called tidal locking. One face of WASP-7b points at the star forever. The other face points away forever. There is no sunrise there, no sunset, no morning creeping across the ground. Just one hemisphere, frozen in permanent daylight, and one hemisphere, frozen in permanent night. Each condition unchanging for as long as the planet exists. Basic physics has a clear expectation for what that arrangement should produce. The day side should bake under constant starlight, with nothing ever interrupting the heat. The night side should sit in cold isolation, cut off from the star entirely, radiating its own warmth away into space, with nothing arriving to replace it. Two hemispheres, two climates, a gap between them wide enough to expect scorched glass on one side and something close to deep freeze on the other. That is not what Webb measured. The day side came back cooler than the models demanded. Not slightly cooler, substantially cooler, hundreds of degrees short of what a planet locked this close to its star should be radiating outward. And the night side, the hemisphere that should have been bleeding heat into the dark with nothing to warm it back up, came back hotter than it had any right to be. The two sides of WASP-107b sit far closer in temperature than physics allows for a world locked in permanent day and permanent night. Something is taking heat from where it should be trapped and moving it somewhere it should never reach. There is only one mechanism capable of doing that at this scale. Wind. Not a breeze, not a storm system confined to one region. A planet-wide current strong enough to physically carry heat from the scorched hemisphere to the frozen one before the temperature gap can even form properly. To close a gap this size, that wind has to move at thousands of miles an hour, and it has to do it constantly, without slowing, without pause, dragging superheated air across the entire circumference of the planet on a loop that never completes. Picture a jet stream the size of an entire world, wrapped completely around the planet like a belt that never sits still, hauling heat from the day side to the night side over and over, every hour, every day, forever. Nothing on Earth compares to a wind system operating on that scale. Our fastest jet streams move air across a fraction of the globe in bursts. This is a single current strong enough to keep an entire tidally locked planet from splitting into two separate climates, running at a speed that borders on absurd, and never once easing off. That raises an uncomfortable question that goes beyond wind speed alone. Something is pushing this atmosphere hard enough to erase the boundary between day and night. And heat transport is only part of the story. The chemistry inside that same atmosphere keeps behaving the same way, refusing to sit still, refusing to settle into anything resembling balance. If the wind will not stop moving, maybe the sky itself has stopped resting too. There is a name for what WASP-107b's atmosphere is doing, and it is not a name most people encounter outside a chemistry classroom. Disequilibrium. Strip away the jargon, and the idea is simple enough to hold in one sentence. Left alone, a mix of gases eventually settles. Reactions run their course, the fast stuff burns off, and whatever is left behind sits quiet, chemically boring, unchanging. That settled, boring state is equilibrium. Disequilibrium is what you get when something keeps interrupting that process. Some force feeding fresh ingredients into the mix faster than the mix can calm down. A sky in disequilibrium is a sky being actively pushed, not a sky simply existing. You do not need to travel to another star system to see this happen. Look up. Earth's own atmosphere is sitting in a state of disequilibrium right now, and it has been for a very long time. Oxygen makes up roughly a fifth of the air around you, and oxygen is a hungry, reactive gas. Left to its own chemistry, it should be binding itself to rock, to metal, to anything willing to react with it, slowly disappearing from the sky, the way a fire eventually runs out of fuel and goes dark. That is not what happens here. Oxygen stays abundant, refilled constantly. And the only reason it stays refilled is biology. Plants and countless smaller organisms are pumping it back into the air faster than chemistry can strip it away. It is being held in an unstable state on purpose, propped up by something alive. That comparison is why WASP-107b matters far beyond its own strange chemistry. Nobody is claiming life exists on a bloated gas giant hot enough to melt silver. What matters is that scientists found disequilibrium there at all. Chemistry actively pushed off balance by rising internal heat, rather than sitting quietly the way an old, settled atmosphere should. Finding it there proves the detection itself works. The method can catch an atmosphere in the act of being disturbed, whatever the cause, from hundreds of light years away, using nothing but starlight passing through a thin sliver of sky. That is the part worth carrying forward. If disequilibrium can be measured on a planet driven by heat alone, the same method should catch it anywhere it happens. Imagine a much smaller world someday, rocky rather than gaseous, sitting in a mild orbit around a quiet star. If oxygen and methane ever turn up together in an atmosphere like that, the finding would demand an explanation, because those two gases destroy each other on contact. Something would have to be manufacturing them faster than chemistry could tear them apart. But that question belongs to a different kind of world than the ones covered so far. Every planet in this story until now has been gas layer after layer with no floor beneath it. Something else entirely is waiting on solid ground. Solid ground is the wrong phrase for what comes next. The next planet has a surface in the sense that gravity holds something together, but nothing about it invites a landing. HD 189733b announced itself to astronomers in an unusual way. Long before anyone mapped its winds or its clouds, this became the first exoplanet in history to have its actual color measured, not modeled, not guessed at from temperature curves. Measured the way you'd measure the color of a wall with your own eyes. And the color that came back was a deep, rich blue, the kind of blue that on Earth would make you think of a calm ocean seen from an airplane window. That resemblance is the cruelest part of this planet. It looks inviting from far enough away. Get closer, and the reason for that blue stops being anything like water at all. Wind is the reason. Measurements put the winds on HD 189733b near 5,400 miles an hour, several times faster than the speed of sound. Read that number again because it is doing more work than it first appears to. A rifle bullet leaving the barrel moves at a fraction of that speed. A jet breaking the sound barrier is a footnote next to this. This is not weather, in any sense Earth has ever produced. This is air behaving like a solid, hurled sideways with enough force to make the word wind feel like an understatement. Now put something into that wind. The blue tint people first mistook for something calm and oceanic comes from a haze of silicate particles, the same rock-forming material found drifting through WASP 107b's sky. Except here, the physics runs differently. On a slower world, that vaporized rock would cool, condense, and fall the way any rain falls, pulled down by gravity in a straight line toward the ground. HD 189733b's winds do not give it the chance. Molten glass condensing in that atmosphere gets caught, immediately seized by air, moving faster than sound, and driven sideways instead of down. There is no gentle drift here, no soft descent. Every particle in that sky moves the way a bullet moves, in a straight, violent line dictated by wind speed rather than gravity. Confirmed carbon dioxide sits inside this same atmosphere, discovered through the same starlight-splitting method that caught sulfur dioxide on WASP 39b and silicate clouds on its cotton candy cousin. That detail matters because it means this world is not just a spectacle of wind. It has real, readable chemistry churning beneath the violence, an atmosphere with the same basic ingredients astronomers look for everywhere, just wrapped around conditions built to destroy anything that enters them. Picture standing on the surface, if surface is even the right word. You would not feel rain. You would feel glass moving faster than a rifle bullet, arriving sideways instead of falling, sandblasting anything solid down to nothing in the time it takes to notice the sky has turned against you. Glass is bad enough. The next planet trades glass for something heavier, something that falls as liquid metal instead. Metal is the wrong material to expect rain from anywhere, and yet WASP 76b builds its entire weather system out of exactly that. This is a planet locked so close to its star that the dayside temperature sits near 2,500 degrees Celsius, a number that does not just melt iron, it vaporizes it, turning solid metal directly into gas the way water turns to steam, except the heat driving this transformation would reduce a steel beam to vapor in the open air. Here is the mechanism, and it runs with a kind of brutal simplicity once you see it laid out. Iron bakes off the surface material on the scorching dayside, lifted straight into gas form by heat with no patience for anything solid. That vaporized iron does not just sit there. Ferocious winds sweep it up immediately, hauling the metal gas across the planet toward the side, facing away from the star. The trip matters because the night side runs cooler, and cooler is exactly what iron vapor needs to stop behaving like a gas. As it crosses into that cooler air, the iron condenses, collapsing back into liquid form. And once it is liquid, gravity does what gravity always does. It falls. Droplets of molten iron down out of the sky on the night side of WASP 76b, a weather event with no equivalent anywhere in our own solar system. Cooler is a relative word here, and it is worth being honest about how relative. The night side runs at least 1,000 degrees Celsius below the inferno on the day side, and on paper, that sounds like real relief. It is not. A drop of 1,000 degrees off, a temperature that hot still leaves conditions nowhere near survivable, nowhere close to anything a human body, a spacecraft hull, or frankly any material we build with, could withstand for more than an instant. The night side is not cold. It is simply the marginally less lethal half of a planet, built entirely out of lethal halves. What makes this world different from a single violent event is that none of it ends. The iron does not fall once and finish. It falls, pools, and the same winds that carried it across the planet in gas form keep circulating, keep dragging fresh vapor from the dayside furnace toward the nightside collection point, over and over, in a loop with no beginning and no conclusion. This is not a storm that will pass. It is a permanent feature of the planet's chemistry. A furnace on one side, manufacturing raw material non-stop, and a cooler side on the other, catching that material every single orbit, forever. Where they're made out of metal, running on a cycle as reliable and endless as any rainstorm on Earth, except every drop of it would kill you on contact, and every gust of wind carrying it moves fast enough to make that a mercy. If a planet can turn iron into rain, cooking metal itself into weather, the next step in this descent stops asking what falls from the sky and starts asking what the ground is even made of. Because past WASP-76b sits a world where the surface itself may never be solid at all, where the entire dayside could be one standing, unbroken ocean of liquid rock. A furnace with weather is one kind of nightmare. 55 Cancri E is a different kind entirely, because here the question is not what falls from the sky, but whether the ground beneath it ever hardens at all. This is a super-Earth, bigger than our own planet but still built from rock rather than gas, and it orbits close enough to its star that surface temperatures may run somewhere between 1900 and 2400 degrees Celsius. Numbers that high stop being useful as a description of heat and start functioning as a description of a phase change. Rock does not stay rock at that temperature. The leading model for what that means is a global magma ocean, an entire hemisphere of the planet held in a molten state, not confined to a crater or a rift the way lava behaves on Earth, but covering the whole dayside as a standing liquid surface. Picture the concept of a coastline, except instead of water meeting land, you have molten rock meeting slightly less molten rock, an ocean with no beach and no bottom you would ever reach, because the bottom is just more of the same furnace continuing downward. A planet baked to those temperatures, sitting this close to its star, should have nothing left in the way of an atmosphere. Radiation at that proximity strips gas away fast, blasting lighter molecules into space until a planet is left bare, a scorched rock with nothing but vacuum pressed against its surface. That is the expectation. It is not what Webb found. Scientists detected carbon dioxide and carbon monoxide surrounding 55 Cancri E, a real atmosphere sitting on a planet that should have lost the ability to hold one long ago. 3 explanations are competing for what is actually going on, and none of them has been ruled out yet. The first suggests a primordial atmosphere, gas the planet held onto from its earliest formation, somehow shielded from the radiation that should have torn it apart over billions of years. The second points toward volcanic outgassing. The interior of the planet venting fresh gas into the sky fast enough to replace whatever radiation strips away. An atmosphere that survives not by resisting destruction. The third theory is the strangest of the 3. The magma ocean itself may be exhaling gas the way a kettle exhales steam. The molten surface constantly boiling off vapor that becomes the atmosphere scientists are reading from hundreds of light years away. Telling these 3 apart from here is not something a single observation can settle. The only way forward is repetition, watching 55 Cancri E cross different points in its orbit, checking whether the atmosphere behaves the same on every pass or shifts, depending on where the planet sits relative to its star. A steady signal points towards something ancient and shielded. A shifting one points toward a surface, actively breathing gas into space in real time. What stays constant either way is the picture underneath the mystery. A planet with no solid ground, only a slow molten skin stretched across a rocky interior, and an atmosphere clinging to it against every expectation of what heat that extreme should allow. Compare that to a world doing the opposite of everything covered so far, not glowing, not radiating, swallowing light instead of producing it. Some planets shine, Trace 2b does not. Scientists measured its reflectivity at less than 1%, which means for every 100 photons that strike this planet, fewer than one bounces back. Everything else gets swallowed. Sit with what that number actually means, because less than 1% slides past too easily on first read. Coal, the blackest common material most people have ever touched, reflects somewhere around 3 to 4% of the light hitting it. Fresh asphalt, laid down dark and glossy before the sun bleaches it, sits in roughly that same range. Trace 2b reflects less light than both of them. A planet the size of Jupiter, sitting in space, absorbing photons more completely than the blackest surfaces we pave our roads with or dig out of the ground. No one has confirmed exactly why. The leading explanation points to unknown chemical compounds drifting high in the planet's atmosphere, light-absorbing substances that current models cannot fully identify, working alongside the sheer heat of a world orbiting close enough to its star to stay in a near-constant scorch. Whatever sits in that upper sky is not reflecting starlight back into space the way clouds do on Jupiter or Saturn. It is drinking it, trapping nearly every photon that reaches the outer atmosphere, and refusing to give any of it back. Now, flip that idea completely. Somewhere else in this same galaxy sits a planet built to do the exact opposite of everything Trace 2b represents. A world that takes starlight and throws almost all of it straight back out, shining instead of swallowing, reflecting instead of absorbing. A mirror where Trace 2b is a void. Somewhere in this same galaxy sits a planet built to do the exact opposite of everything Trace 2b represents. LTT 9779b is an ultra-hot world roughly the size of Neptune, locked into an orbit so tight that a full year there lasts only 19 hours. Start to finish, the entire trip around its star wraps up faster than a single day back home. That kind of closeness should mean one thing above all else: heat with nowhere to go, an atmosphere baking under constant starlight and radiating that heat back out as a dim, dark glow. The same way. That is not what scientists found. LTT 9779b reflects around 80% of the light striking it, the highest reflectivity ever recorded for any exoplanet. Think about what that number is asking you to accept. This is not a cool, calm world, coated in the kind of soft white clouds that make Venus glow bright in our evening sky. This is a planet baking under extreme heat, close enough to its star to qualify as one of the hottest worlds ever measured, and it is behaving like a mirror instead of a furnace. 8 out of every 10 photons that hit this planet bounce straight back into space, untouched, unabsorbed, as if the atmosphere itself refused to let the heat in. The mechanism responsible sits in the clouds themselves, and the clouds are not made of anything resembling water vapor. Silicate and metal, the same raw ingredients cooked into vapor on WS-107b and dragged sideways into glass storms on HD 189733b, condense here into something different entirely. High in LTT 9779b's atmosphere, that vaporized rock and metal cools just enough to form tiny reflective droplets, a layer of shimmering material acting less like a cloud and more like a polished surface stretched across the entire dayside. Starlight hits that layer and scatters straight back out before it ever has the chance to soak into the deeper atmosphere and turn into heat. That creates a contradiction sitting right at the center of everything scientists thought they understood about planets this hot. A world lot this close to its star, cooking under this much starlight, should be glowing with absorbed heat, radiating that energy back out the slow way through infrared warmth rather than direct reflection. LTT 9779b is doing something else. It is shining instead of glowing, deflecting the very energy that should be defining its temperature. That single fact reaches further than one strange planet. If clouds built this way can reflect away enough starlight to change a planet's basic energy balance, then some worlds sitting close to their stars might run cooler than distance alone would predict, while others, assumed to be comfortable, could be hiding a harsher reality beneath clouds that trap rather than reflect. Reflectivity itself becomes a variable nobody accounted for. Every planet covered until now earned its place through violence, through heat, wind, or pressure, extreme enough to kill instantly. What comes next is a different kind of impossible. A world whose danger comes not from what it is doing, but from how long it has managed to keep existing at all. Age is where this next planet breaks the rules. Not heat, not wind, not pressure. TOI 561b has been sitting in orbit for something close to 10 billion years, making it one of the oldest rocky planets ever confirmed. Earth itself is only about 4.5 billion years old. This planet was already ancient before our own solar system had finished forming, a rocky world that has been orbiting its star since the Milky Way itself looked nothing like it does now. You would expect a planet that old to have gone quiet a long time ago, cooled down, settled. Instead, TOI 561b sits close enough to its star that surface conditions likely support a global magma ocean, the same kind of molten, unbroken surface found on 55 Cancri E, except here that furnace has been running for roughly twice the age of our entire planet. 10 billion years of continuous heat, and the ground still has not finished melting. Here is where the real contradiction sits. Every model built for atmospheric escape says a planet this old, this close to its star, should have lost whatever gas it once held long ago. Billions of years of radiation pouring off a nearby star strip lighter molecules away first, then heavier ones, until nothing is left but bare rock exposed to open space. That process does not take 10 billion years to finish. It takes a fraction of that time. By every rule built from studying younger systems, TOI 561b should be a stripped, airless cinder by now, a scorched surface with nothing above it but vacuum. It is not. TOI 561b appears to retain a volatile envelope, some kind of atmosphere clinging to a surface that should have lost the ability to hold 1 billions of years before now. Not a thick, stable sky like Earth's. Something thinner, something that by every existing model has no business surviving this long against this much radiation, and yet the readings keep coming back the same way. Gas, where there should be nothing. That single fact forces a bigger question than one old planet's stubborn atmosphere. If a rocky world this ancient can hold on to gas against odds this steep, then the standard timeline for how fast atmospheres disappear may be wrong or incomplete, built on assumptions that only hold for younger systems closer to what we already understand. The deeper implication reaches further than atmospheric physics alone. If rocky planets like this one were already forming and surviving this early in the galaxy's history, then the process of building solid worlds out of gas and dust started earlier than most models assumed, stretching the timeline of rocky planet formation back toward the very beginning of the Milky Way itself. Every planet covered so far has pushed some boundary of heat, pressure, or darkness. Kel 9b pushes past a boundary that should not exist for a planet at all. Dayside temperatures on this world reach roughly 4,300 degrees Celsius. That number needs a second look, because it is not just hotter than any planet has a right to be. It is hotter than many red dwarf stars, the small dim suns that make up most of the stars in the galaxy. Stand next to certain stars, and Kel 9b would still be putting out more heat than the star itself. The orbit explains part of why. Kel 9b circles its host star once every roughly 1.5 days. That is not a year in any familiar sense. That is barely enough time for a planet to complete one full loop before starting the next, locked into a rhythm so tight that distance stops offering any kind of shelter from the star's output. Being that close means the tidal forces at work are extreme, gravity gripping the planet hard enough to stretch and flex it the way Jupiter flexes its own moons. Except here, the gravitational grip is paired with a host star that runs far hotter and far more energetic than anything in our own solar system. The combination of closeness and tidal stress keeps pouring energy into the planet with no real way for it to cool off between exposures. Here is where the chemistry stops behaving like chemistry anywhere else. At 4,300 degrees, molecules do not just struggle to survive, they fail outright. Heat on the day side is intense enough to rip apart molecular bonds directly, tearing hydrogen molecules apart into raw atoms before they ever get the chance to hold a stable shape. Those atoms do not just vanish though. Winds carry them around toward the night side into cooler air, where the temperature finally drops low enough for those same atoms to recombine, reforming back into molecules again. Then, the rotation carries that same material back toward the day side, back into heat that will tear it apart all over again. This is not an atmosphere in any steady state. It is a cycle of constant chemical death and rebirth. Molecules destroyed and reassembled over and over, planet-wide, without pause, because the planet itself never stops being torn between one hemisphere hot enough to erase chemistry and another just barely cool enough to let it happen again. But heat alone, however extreme, is not the only way a planet can come apart. Some worlds do not just burn under their star's glare. They lose themselves entirely, streaming their own atmosphere away into space in plain sight, visible from here as something closer to a tail than a sky. Some planets do not die quietly. HD 209458b was the first to make that death visible, a hot gas giant orbiting close enough to its star that astronomers caught something no one expected to find on a planet at all: a tail. Not a metaphor, not a computer model's guess at what might be happening. A real, streaming trail of gas pouring off the planet and stretching out behind it the way a comet's tail streams away from the sun, except this is not a chunk of ice and dust. This is an entire planet, bleeding its own sky into open space in a shape telescopes can actually resolve. The mechanism behind it has a name, and the name is almost too calm for what it describes: hydrodynamic escape. Strip the term down, and the idea is simple enough. Heat from the star hits the upper layers of a planet's atmosphere so hard that those gas molecules stop behaving like a sky and start behaving like an exhaust, moving fast enough to outrun the planet's own gravity entirely. Gravity supposed to hold an atmosphere down the way it holds anything else in place. Get close enough to a violent enough star, and that grip stops being strong enough to matter. The outer atmosphere simply leaves, lifted off the planet and swept into space by the same starlight that should, in a calmer system, just be warming the ground. Rauch-Lobe overflow makes the picture worse. Every planet sits inside an invisible boundary defined by the balance between its own gravity and its stars, a kind of gravitational territory line. Get close enough to the star, and part of the atmosphere can drift past that line entirely, no longer belonging fully to the planet or the star, caught in the pull of both, until the star's gravity simply takes it. That is not an atmosphere being stripped by force from outside. That is an atmosphere losing its own claim to material that used to be unquestionably its. What makes these worlds different from everything covered before is the tense. Every planet in this story until now was described in the present, a fixed condition, a permanent feature of extreme chemistry or wind or heat. These comet-tailed worlds are not fixed. They are caught mid-collapse, observable evidence of atmospheric death happening in real time rather than something modeled on paper and assumed to be true. Astronomers are not calculating what should happen to a stripped planet eventually. They are watching it happen, gas visibly leaving, right now, streaming into the dark in a shape any decent telescope can trace. Picture a spool of thread with one end caught on something moving away from it. The thread does not snap all at once. It unwinds steadily, continuously, the spool growing thinner with every pull, until eventually there is nothing left to give. That is what is happening to worlds like this. Atmosphere pulled loose one layer at a time, visibly thinner with every observation, a planet being slowly unwound by its own star. That raises an unsettling question of its own. If a planet can lose an atmosphere it clearly earned orbiting a living, blazing star, what happens on a world that should never have had an atmosphere to lose in the first place, circling something that is not a star anymore at all, but the corpse of one? That corpse has a name. PSR J2320 to 2650b is a planet roughly the mass of Jupiter, and it does not orbit a star at all. It orbits a pulsar, the leftover core of a star that already died in a supernova, collapsed down into something small enough to hold in your imagination and dense enough to break it. This is not a planet circling a sun that will one day grow old and fade. This is a planet circling a corpse that already finished dying and kept right on spinning. Here is what a pulsar actually is, because the word does a poor job of preparing you for the reality. Take a star several times heavier than our own sun and collapse it down to something roughly the size of a city, maybe 12 miles across, packing all that original mass into a ball you could nearly drive across in an afternoon. That collapse does not slow the star's spin. It speeds it up the same way a skater spins faster, by pulling their arms in tight. The result is a dead star spinning hundreds of times every second, whipping a beam of radiation around like a lighthouse on the fastest rotation imaginable, sweeping past anything in orbit again and again without pause. A planet sitting inside that beam should not have an atmosphere left to speak of. Radiation at that intensity, delivered in a relentless repeating sweep, reads like a death sentence for anything as fragile as a sky. And yet, when scientists pointed Webb at PSR J 2320 to 2650b, they found an atmosphere there anyway, one that had no business surviving the environment it was sitting in. What that atmosphere is made of is where the real strangeness sits, Instead of the hydrogen and oxygen compounds that dominate nearly every other atmosphere covered so far, water vapor, carbon dioxide, the familiar chemical vocabulary of gas giants and lava worlds alike, this planet's sky reads back as helium and carbon. A completely different chemical language, built from different raw ingredients, surviving in conditions unlike anything else in this entire catalogue of hostile worlds. That is the part worth sitting with. An atmosphere exists here, bathed constantly in the radiation of a stellar corpse, built out of chemistry that does not match a single other planet in this story. Not a variation on a familiar theme. Something genuinely apart, chemically unlike anywhere else humans have ever looked. Every planet up to this point has orbited something recognizable, a living star, however violent or strange. This one orbits a grave, and with that, the exoplanets end here, at least for now, because there is a hidden ocean far closer to home, sitting quietly under ice in our own solar system, that has been keeping a secret for a very long time. That grave gives way now to something wetter. Somewhere out past Mars, orbiting a planet that dwarfs our own by a factor most people never stop to picture, sits a moon smaller than Earth's own moon. Cross a highway on foot, and you have covered more distance than this moon spans across its face. And yet, locked beneath its frozen shell, Europa holds something that should not fit inside an object this small twice the water. Not twice the water of a lake, or a sea, or even the largest ocean on Earth alone. Twice the water contained in every single ocean on this planet, combined. The Pacific and the Atlantic and the Arctic and all the rest, doubled, and packed into a moon you could nearly walk across in a long weekend. The first hint that something was wrong with this picture came from the surface itself, and it came from an absence rather than a presence. Every other rocky or icy body in the solar system wears its history the same way. Craters, piled on more craters, a record of billions of years of impacts with nothing around to erase them. Our own moon looks like a battlefield for exactly that reason. Mercury looks the same way. Mars, despite everything else going on there, still carries the scars. Europa does not. Its surface is smooth, startlingly young, carrying only a scattering of impact marks where thousands should exist by every normal rule of solar system aging. A surface that clean is not a surface that has simply avoided getting hit. It is a surface being repaved over and over by something working from underneath. Look closer at that smooth shell. The story gets stranger. Scattered across Europa's ice are regions scientists call chaos terrain, and the name fits exactly what it describes. These are not clean cracks or simple fractures. These are places where the ice has broken into enormous rafts, drifted out of position, tilted against each other, and then frozen back into place at odd angles, like a frozen lake that shattered in the middle of a storm and locked solid mid-collapse. Ice does not behave that way, sitting on top of solid rock. Ice behaves that way when it is floating, breaking apart, and refreezing above something liquid underneath it. Chaos terrain is not a guess about what might be under Europa's surface. It is the visual signature of an ocean caught in the act of disturbing the shell above it. Confirmation came from something that had nothing to do with cameras at all. When the Galileo spacecraft passed close to Europa in the 1990 seconds, it carried instruments built to read magnetic fields, not to photograph anything. Jupiter's own magnetic field is immense, sweeping across all of its moons constantly. And as Galileo measured how that field behaved near Europa, It found something that only made sense if a very specific kind of material sat underneath the ice. A global layer of salty liquid water conductive enough to generate its own magnetic response, reacting to Jupiter's field the way a real ocean would, and nothing else could. No drill touched the surface, no probe broke through. An ocean was confirmed on a moon hundreds of millions of miles away purely by reading an invisible magnetic signal, water announcing itself through physics alone. Depth is where the scale of this ocean stops being an abstract idea. Earth's deepest point, the Mariana Trench, plunges close to 7 miles down, a place so extreme that only a handful of vehicles in history have ever survived a trip there. Europa's ocean is estimated to run far deeper than that trench, in places more than 10 times as deep, an entire sea stacked higher than our planet's most extreme depth allows, wrapped around a moon. An ocean this size, this deep sitting, this far from the sun, raises an obvious problem. At Europa's distance, sunlight barely qualifies as warmth at all. So what exactly is keeping all that water from freezing solid? The answer sits in Jupiter's grip, and it does not work the way you'd expect gravity to work at all. Europa does not circle Jupiter in a clean, even circle. Its orbit is slightly stretched into an oval, pulled off, true by the gravity of neighboring moons, and that small distortion turns out to be the whole reason this moon is not a solid block of ice straight through to its core. As Europa swings closer to Jupiter along that oval path, gravity yanks harder on it. As it swings back out to the far end of the same oval, that pull relaxes, closer, pull tight, farther, released. That cycle repeats every 3.5 days, over and over, for as long as Europa has existed. Take a rubber ball and squeeze it in your fist, then let go, then squeeze it again fast, over and over for a solid minute. Stop and touch the rubber. It is warm. Nobody lit a match under it. Nobody plugged it into anything. That heat came from nothing, but the act of bending the same material again and again, until the friction inside it had nowhere to go but out as warmth. Jupiter is doing that to an entire moon. Europa's ice flexes with every orbit, its rock flexes beneath the ice, and all of that repeated bending generates real heat deep inside. The same way a bent rubber ball warms in your hand, that is the furnace keeping Europa's ocean liquid, hundreds of millions of miles from a sun too weak to do the job on its own. No flame, no fuel, just squeezing over and over, forever. Here is the part that should unsettle you. Left alone, gravity does not keep orbits stretched into ovals. Left alone, an orbit relaxes into a circle over time, the way anything under strain naturally settles toward its most stable shape. If that happened to Europa, the flexing would stop. No flexing means no friction. No friction means no heat. No heat means that ocean freezes solid, the whole engine shutting down permanently. That has not happened, and the reason involves 2 other moons that have nothing directly to do with Europa's own path around Jupiter. Io circles closer to Jupiter than Europa does, and Ganymede circles farther out, and the 3 of them move in a locked rhythm. For every 1 loop Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. That precise ratio means the 3 moons keep lining up in the same configuration again and again, and each time they do, their gravity tugs on each other just slightly. A small pull, repeated at exactly the same point in the cycle, every single time, stacks up the way a series of perfectly timed pushes on a swing sends it higher and higher. Those repeated tugs, are what keep yanking Europa's orbit back into its oval shape every time gravity tries to smooth it into a circle. That means Europa's whole ocean depends on a rhythm involving 3 separate moons that have no relationship to each other beyond this locked orbital beat. Break that rhythm, and the flexing stops. Stop the flexing, and the heat fades. Machine. This delicate, keeping a hidden sea liquid for billions of years, running on nothing but timing. But knowing the ocean stays warm is different from knowing what that warmth actually does once it reaches the ocean floor. And that is exactly where the newest research has started pulling the picture apart. In early 2026, a team of researchers ran the numbers on Europa's rocky core and reached a conclusion that pulled the rug out from under one of the most exciting parts of the whole picture. Their models suggest Europa's seafloor might be too rigid, too stiff, too geologically locked down to crack open the way scientists had hoped. And if that rock cannot crack, then a specific kind of activity assumed to be happening at the bottom of that ocean may simply not be happening at all. Here on Earth, the ocean floor holds structures called hydrothermal vents, and the version most people picture first is what scientists nicknamed black smokers. Towers of mineral rock rising off the seafloor, sometimes taller than a house, with scalding water blasting out of their tips, dark and cloudy with dissolved metal, billowing upward like smoke pouring out of a chimney built entirely underwater. Surrounding those vents is not empty seabed, it is a crowd. Tube worms taller than a person swaying in total darkness, blind shrimp packed together in the mineral haze, crabs picking through bacterial mats coating every surface nearby. An entire ecosystem, dense and thriving, running with zero sunlight anywhere near it, powered instead by chemistry pouring straight out of the planet's own interior. The hope for Europa was that its ocean floor might be doing the same thing. Rock meeting water under enough heat and pressure to crack, circulate, and pump out the same kind of mineral-rich chemistry that feeds those vent communities on Earth. That is what would turn Europa's ocean from a passive body of water into an active chemical engine capable of feeding life. The 2026 modeling throws that assumption into real doubt. If the tidal flexing keeping this moon warm is concentrated more in the ice shell than in the rock below it, the seafloor itself could be sitting cold and rigid, sealed shut, incapable of the fracturing that lets water and stone actually mix. That does not mean the ocean is left with nothing. A competing model points somewhere else entirely for the ocean's chemistry. Starts at the surface rather than the floor. Jupiter's radiation constantly bombards Europa's ice, and that bombardment does something specific to the water molecules locked inside it. It breaks them apart, and in doing so, it manufactures oxidants, reactive compounds that could, in theory, sink slowly downward through the ice shell over enormous stretches of time, eventually reaching the ocean and feeding it from above instead of below. A trickle instead of a vent. A slow drip of chemistry rather than a violent chemical furnace. Both pictures remain on the table right now, and neither one has won. One version gives you an energetic ocean, fed from beneath by real geological heat, chemically rich enough to plausibly support something alive. The other gives you a quieter ocean, thinner, colder at the bottom, surviving on whatever chemistry manages to seep down from the irradiated surface across millions of years. This is not settled science dressed up as uncertainty for effect. Scientists studying Europa right now genuinely disagree about which of these two oceans is the real one. Contrast that against a smaller moon orbiting a different planet entirely, where this same question was not left to modeling and disagreement. A spacecraft flew straight through the answer. A spacecraft flew straight through that answer, and it did not have to guess at anything. Enceladus is small even by moon standards, a fraction of Europa's size, tucked in orbit around Saturn rather than Jupiter. Where Europa keeps its ocean locked behind a sealed shell that scientists can only interpret from a distance, Enceladus does something almost generous by comparison. It vents its ocean directly into space, in plain view, close enough for a spacecraft to fly through and taste. Cassini did exactly that. Rather than orbiting at a cautious distance and reading magnetic fields the way Galileo did at Europa, Cassini flew directly through the plumes erupting from Enceladus's south pole, passing straight through jets of material blasting up from cracks in the ice and out into open space. That is not an indirect measurement pieced together from a magnetic wobble. That is a spacecraft physically passing through ocean water, lifted straight off the source, sampling it in real time the way you might catch spray off a wave. What Cassini found inside those plumes settled questions Europa still cannot answer. Molecular hydrogen showed up in the readings, and molecular hydrogen is not something that appears in ocean water by accident. It is produced specifically through hydrothermal reactions, the same chemical process happening at Earth's own seafloor vents, where hot water reacting with rock manufactures exactly this kind of gas. Alongside the hydrogen, Cassini detected organic compounds drifting in the same spray, carbon-based molecules hiding the plume material out into space. Together, that combination is not ambiguous. It is direct chemical evidence of an ocean floor doing real, active geology, water and rock, interacting hard enough to produce the same chemistry that feeds entire ecosystems in Earth's deep sea. Set that against everything covered about Europa. Europa's seafloor sits behind a debate. One model suggesting a warm, cracked, chemically rich ocean floor. Another suggesting a colder, sealed, geologically quiet one with no way yet to confirm which picture is real. Enceladus does not carry that same uncertainty. Cassini did not model the plumes or infer them from an orbit hundreds of miles away. It flew through them directly and read the chemistry firsthand. There is no competing hypothesis here about whether hydrothermal activity might be happening. The spacecraft already caught it in the act. That distinction matters far beyond one small moon's chemistry. Enceladus proves something Europa alone cannot yet prove, which is that ocean worlds with genuine active hydrothermal engines are not a hopeful theory. They are a confirmed category of object that exists in our own solar system, sitting a few 100 million miles from Earth. Actively producing the exact kind of chemistry life depends on here at home. Europa might turn out to belong to that same category, eventually. Right now, Enceladus, the one that has already shown its hand. And once one moon confirms that hidden oceans can run this active this far from the sun, the obvious next question is how many other worlds out past the familiar planets might be hiding the same kind of sea. Titan and Pluto, worlds that look nothing alike on the surface, both carry hints of exactly that. Titan looks nothing like Enceladus, and it looks nothing like Europa either. This moon of Saturn is large enough to carry its own thick atmosphere, and beneath that hazy orange sky sits something no other body in the solar system can claim. Lakes, rivers, seas spread across the surface in plain sight, filled not with water but with liquid methane and ethane chemistry that behaves like nothing else humans have ever studied up close. Rain falls there. Rivers carve channels into the ground there. An entire weather cycle runs on hydrocarbons instead of water, cold enough that methane behaves the way water behaves on Earth, evaporating condensing, falling, pooling. For years, the working assumption was that Titan hid something familiar underneath all that exotic surface chemistry, a global ocean of water and ammonia sealed beneath the ice, similar in shape to what sits under Europa. A 2025 reanalysis of older orbital data complicated that picture considerably. Rather than one continuous global sea, the interior now looks slushy, uneven, holding localized pockets of liquid scattered through a mix of ice and softened material, rather than a single unified ocean wrapping the whole moon. Not a clean layer of water sitting beneath a clean layer of ice. Something messier, a mush of partially frozen material with liquid caught in pockets rather than flowing as one connected body. Pluto raises a stranger version of the same question, because almost nothing about Pluto should allow for liquid water at all. This is a small, distant world, sitting so far from the Sun that surface temperatures sit far colder than anywhere covered so far in this entire journey. And yet its surface carries geological features, fractures, ridges, signs of past expansion that only really make sense if something liquid moved beneath the crust and pushed outward as it refroze. The leading explanation points to a combination of two things working together: leftover heat from Pluto's own formation, radioactive decay ticking along slowly inside its core, and antifreeze compounds mixed into whatever water sits down there, chemistry that lowers the freezing point far enough to keep a hidden ocean liquid at temperatures that would otherwise turn it to solid rock-hard ice. Put Titan and Pluto next to Europa and Enceladus, and a pattern starts to emerge that reaches past any single moon. 4 bodies, 4 completely different sizes, 4 different distances from the Sun, and every one of them appears to be hiding liquid somewhere beneath a frozen shell. That is not 4 rare exceptions. Subsurface oceans may not be some strange, unlikely oddity confined to 1 or 2 special moons. They may be common, scattered across cold, distant worlds throughout the outer solar system, hidden simply because nobody had reason to look until recently. Push that idea further out, past every planet and moon, still bound to a star at all, and the isolation only deepens. Somewhere out there drift worlds with no sun to orbit in the first place. Worlds with no sun at all are not a rare footnote in this story. They are a whole category of planet, and calling them planets stretches the word almost as far as Kelt 9b did from the other direction. A rogue planet is a world with no star to orbit, period. Some formed the normal way, coalescing out of gas and dust around a young star, and then got kicked out entirely, flung loose by a gravitational encounter with a passing star or a larger sibling planet, shoving them out of the system for good. Others may never have belonged to a star in the first place, condensing directly out of a collapsing cloud of gas the same way a star does, just without gathering enough mass to ignite. Either way, the result is the same. A planet, drifting completely alone, with nothing anywhere nearby to call its own sun. Every world covered up to this point has had some relationship with a star, even the worst of them. Even Kelt 9b, scorched down to its bones, still had a sun defining its entire existence. A rogue planet has none of that. No sunrise, no dayside, no warmth arriving from anywhere outside itself, ever, for the entire span of its existence. The cold on a world like this runs deeper than anything tied to a star, because every planet discussed so far, however far out, however dim its sun, still receives something. Rogue planets receive nothing. Whatever temperature they hold, they generate entirely on their own, floating through permanent, total darkness with no external light source anywhere close enough to matter. Finding something that gives off no light of its own, sitting in the black between stars, sounds close to impossible, and in the most literal sense, it should be. Scientists manage it through a method called gravitational microlensing, and the idea works almost by accident. When a massive object, even one invisible and unlit, happens to pass directly between Earth and a distant background star, its gravity bends the star's light path just enough to briefly brighten it, a short flicker that would otherwise make no sense. That flicker is the entire signal. Astronomers are not looking for the planet directly. They are watching for the way its gravity briefly disturbs light from something else entirely, catching an invisible object purely through the shadow of its influence. That leaves an open question sitting underneath every rogue planet ever found this way. Total isolation does not automatically mean total deadness. Some of these worlds may still generate internal heat from their own formation, the same slow leftover warmth cooking inside Pluto's core. And if that heat holds steady long enough, a rogue planet could theoretically keep a subsurface ocean liquid sealed beneath ice entirely on its own. The scale involved is where this gets difficult to hold in your head at all. Current estimates suggest potentially billions of these worlds drifting through our galaxy, alone, unlit, unmapped, invisible to nearly every method astronomers normally rely on. Every planet covered until now has had a name, a star, a known position. Most of these do not, and most of them never will. Step back now from any single planet, look at the whole shape of what you just walked through. Venus should have stayed a twin of Earth and instead cooked itself into a furnace. Jupiter offered no floor to stand on. WASP 107b bent its own interior heat into a machine that erases methane before it can form. WASP 76b turned iron into weather. TOE 561b held onto a sky it had no right to keep for 10 billion years. None of these worlds broke any law of physics to do what they did. Physics never bent for any of them. What bent over and over was human expectation. Every model built to describe these planets started from the same place, the same small sample size, the 8 worlds and handful of moons sitting in our own solar system. That sample taught scientists what a gas giant should look like, what an old planet should have lost by now, what temperature should do to a molecule. Then, telescopes turned toward other stars, and those models kept failing, quietly and repeatedly, one planet at a time. Sulfur dioxide, surviving heat that should have destroyed it instantly. An atmosphere clinging to a planet that had no business keeping one. A world reflecting light the way nothing that hot should reflect light. Not one of these was a single lucky anomaly. Each was a pattern repeating itself across a different star system, a different mass, a different distance from home. Here is the part worth sitting with. None of this was shock for its own sake. Every impossible planet covered in this story forced actual scientists to actually revise actual models, not just marvel and move on. WASP 107b is missing. Methane pushed researchers to build internal heating mechanisms into their atmospheric models that had not existed before. TOE 561b's stubborn atmosphere is forcing a rethink of how fast atmospheric escape really runs on ancient, close-orbiting rocky worlds. Each planet that broke a prediction did not just embarrass the prediction, it replaced it with something closer to true. Multiply that pattern across the thousands of exoplanets catalogued so far, each with its own atmosphere, its own chemistry, its own violent or quiet history, and a different picture starts to form than the one most people carry around by default. There is no single mold that planets fall into, no universal blueprint waiting to be confirmed once enough data comes in. What the growing library of exoplanet atmospheres actually shows, planet after planet, star system after star system, is that diversity is not the exception to some underlying rule. Diversity is the rule. And once you accept that the universe manufactures this much variation without hesitation, a colder question follows right behind it. If planets can differ this wildly, this completely, what does that same diversity say about the odds of finding anything alive out among them at all? Count up every way a planet has tried to kill something in this story, and the list stops looking like a coincidence. Heat did it on Venus, trapping itself until lead would melt in the open air. Pressure did it on Jupiter, crushing anything falling inward long before it found a bottom that doesn't exist. Wind did it on Neptune and on HD 189733b, fast enough in one case to flay skin and in the other to turn glass into gunfire. Darkness did it on Trey 2b, swallowing light so completely the planet all but erases itself from view. Radiation did it around a pulsar, bathing an atmosphere in a beam that should have stripped it bare in an instant. Cold did it on the rogue planets, worlds with no sun at all, drifting through a temperature no star ever touches. That's not one mechanism repeating itself across different worlds. That's 6 or 7 completely separate ways to end anything alive, discovered independently on planets that have nothing to do with each other beyond existing. Somewhere in this same galaxy, the universe didn't need to reuse a single idea. It built new methods every time. Heat here, pressure there, radiation somewhere else entirely. Each one sufficient on its own to finish the job without help from any of the others. Set that against Earth, and the comparison gets uncomfortable fast. This planet sits inside a narrow band of distance from its star, close enough for warmth, far enough to avoid a runaway greenhouse like the one that cooked Venus. It carries a magnetic field strong enough to deflect the worst of what its star throws at it. It holds an atmosphere thick enough to breathe, but thin enough not to crush. It has liquid water sitting right at the surface instead of buried under 15 miles of ice or boiled off into space. None of those conditions had to align. Each one is a separate requirement, and Earth happens to meet all of them at once in a universe that has shown world after world just how many ways there are to meet none of them. That isn't a comforting thought, and it shouldn't be dressed up as one. It would be easy to end here with some line about how rare and precious that makes this planet, and stop there feeling good about it. But that's not what the data actually says. The data says the odds of any single world landing inside every one of those narrow requirements at once are not obviously in anyone's favor. Nothing measured across this entire journey argues that Earth's balance is guaranteed to repeat itself elsewhere. It just says that it happened once here, and that everywhere else humans have managed to look, it hasn't happened the same way twice. Sit with that instead of resolving it. Because right now, reading this, you're not standing on one of those other worlds. You're standing on the one world in this entire story that never came up as a warning. Somewhere out past Mercury's orbit, on a planet twice the size of Jupiter, iron still falls sideways through winds strong enough to carry molten metal instead of rain, cooling into droplets before it ever reaches whatever ground WAS 76b actually has. Somewhere past that, locked under 15 miles of ice, Europa is still holding an ocean twice the size of every sea on this planet combined, keeping whatever secret it's keeping in total darkness that no camera has ever reached. And somewhere else entirely, Trace 2b sits in its own orbit doing nothing at all, absorbing every photon that touches it. A planet so black it would vanish even lit directly by its own star. All three of those worlds exist right now in the same galaxy, under the same physical laws, built from the same handful of elements that make up everything else out there. Nothing about the universe prevented any of them. Nothing about the universe was obligated to also build this one. You are sitting somewhere with breathable air pressing gently against your skin at a pressure your body doesn't have to fight. There is liquid water within walking distance of wherever you are right now. The ground under you isn't lava, isn't metal vapor, isn't crushing you flat, isn't offering no floor at all. None of that was inevitable. Every planet covered in this story is proof that it wasn't. The universe had every reason to make this planet like one of the others. It didn't.